So yeah, I'm Jessica. I'm a postdoctoral researcher here at SOFIA, and I'm going to be talking a little bit about the work I did with Dario Fata, who gave the previous talk to investigate the C plus emission in a nearby galaxy, NGC 7331. So this is the C plus map from NGC 7331, and I'll be using that as an example for what C plus emission can tell us about ISM conditions in nearby galaxies, and just giving a little bit of a kind of tutorial of how we did the measurements that we did. I may get interrupted by my cat in this talk. He's been a little talkative this morning, so if that happens, I apologize, and we'll just continue through, hopefully. I've also put these slides on my webpage, which is down there on the research page. There's a list of the talks I've given recently, and this one is there with these slides if you'd like to check them out. So jumping in, just as a quick outline, my plan is to start talking with a little description of why we might be interested in measuring the C plus 158 micron line, so what it is and why it's important to studies of the interstellar medium. How we can use the SOSPEX tool, which Dario showed a little bit, to analyze spectral maps from FIFI. So showing just how we can compare spectra and photometry in SOSPEX, compare different spectral cubes in SOSPEX, and then also extract flux using SOSPEX. And then I'll finish up by talking a little bit about some of the potential diagnostics we might be interested in comparing C plus to, including infrared emission, PAH emission, and CO emission. So that's my basic plan. Again, this is NGC 7331, so this is the galaxy that we looked at and what I'm going to be using as an example for most of the data analysis I did in this talk. So first off, just why might we be interested in studying C+? So C+ is often the brightest observed emission line from a galaxy, and that's just showing, this is just an SED kind of highlighting that fact where we can see this C+ emission line kind of rising above, having a very high luminosity. And this is due to a couple different reasons, part of which is because C+ is this great far infrared line, so it's able to pass through dust and gas within a galaxy with minimal attenuation. So even though there's a lot more H-alpha, or there's a lot more hydrogen in galaxies, so we might expect the H-alpha emission to be the brightest. H-alpha is, of course, an optical line, so it gets attenuated by dust and gas, where C+ is a far infrared line, so it's able to pass through. Because it's so bright, it's detectable in both the local universe through observatories like SOFIA, as well as the high redshift universe through millimeter observatories like ALMA. So these are just two examples of C+ detections from redshift of approximately 7 sources. There's quite a few of these, and we're getting more and more as ALMA from redshifts of about 4 to, I think I've seen even a redshift of 9 C+ detections. So we're really seeing a wide range of these detections. So there's this hope that we can use C+ emission to analyze ISM conditions in galaxies both near and far and get a better idea of how galaxies evolve over cosmic time. It's also a really important PDR cooling line. So this is just a very simple model of a star forming region that I've put together, where in the center we have our hot young O and B stars that are emitting a lot of UV photons and ionizing the gas around them. And then surrounding our H2 region with O and B stars, we have a PDR, where there's going to be neutral hydrogen as well as ionized carbon. So carbon has a lower ionization potential than hydrogen at 11.3 electron volts, so sub-Rydberg, which allows it to exist in neutral phases of the ISM, which is another reason why it's so bright. It's everywhere. And it provides one of the really important cooling channels for PDRs. So PDRs get heated up by these UV photons from young stars. In order for them to radiate energy away, they need long wavelength far infrared emission lines, like the 158 micron line, that can penetrate the dust and radiate that energy away. So it's often used as a way of kind of diagnosing the heating and cooling balance within PDRs, as well as other phases of the ISM potentially. And finally, there's this hope that we can use C+ as a measurement of star formation rate because of that. So in that previous slide, I mentioned that C+ was this important PDR cooling line. So if PDRs are mostly heated by young stars and they're mostly cooled by C+, and we have an approximate energy balance in our PDR, we would expect C+ cooling to directly trace infrared heating, and therefore C+ to be a pretty reliable star formation rate indicator. And there's been some issues with this. I'll talk about that a little bit more towards the end, where I show our results, but there is some hope that we can use C+ as a star formation rate indicator, as this plot from Herrera-Camus 2015 shows. There's a pretty good relationship between the surface brightness of the C+ emission and the surface density of star formation rate, especially after an infrared correction to the C+ emission. So hopefully with all of this, I've convinced you that it's worthwhile to study the C+ line, since it is such a powerful diagnostic tool of the interstellar medium and can be measured across cosmic time. So now I'm going to get a little bit more into how we can do this using SOFIA data, and specifically the SOSPEX tool, which Dario showed a little bit in the previous talk. So SOSPEX is a great interactive GUI that can allow you to analyze FIFI-LS, GREAT, and PAX spectra. There's a link here to where you can download it. I also made a little QR code if you want to take a picture of that, scan it, and it should take you to that link. And SOSPEX is especially powerful because it allows you to compare your spectra to photometry and also extract these emission line fluxes. So I'm just going to I have a few quick videos showing a few simple things you can do with SOSPEX, but I highly encourage you to download this and try it out yourself, because it's a very useful tool for understanding your data. So just to get started, I'm going to try to make this a little better quality, hopefully. So this is just, I have a little environment for loading SOSPEX, and when I do load it, I can go in and grab some FIFI-LS data I already have, and it just brings it up, and I can see this is, again, I'm going to be using my NGC 7331 data, but I can slide around through the slices of the spectral cube to see the differences in wavelength position, as well as move my cursor around to see how the spectra looks different as a function of position. So this allows me to pretty quickly get an idea of what the data for my galaxy looks like, where the C+ emission is peaking, and how it changes as a function of position within our galaxy. So that's just right away loading my spectral cube with SOSPEX. I can already get an idea of what kind of data I'm going to get by looking at the C+ emission from my galaxy. So once I've got my data loaded in, I might want to compare to photometry, because the spectra can be a little difficult to tell what exactly we're looking at. So in order to be able to really see where in the galaxy I'm looking, let me just back up. So I'm going to import another image. So I'm going to be using data I already downloaded. So just going to an IRAC channel 4, so 8 micron data, which pops up in another tab on SOSPEX. So now I can see the galaxy in 8 micron light from the IRAC data, where it's a little easier to see. NGC 7331 has this bright molecular ring, infrared bright molecular ring. And it's a little easier to see that, as well as the central nuclear region and some of the rings within the galaxy. So now I can get a better idea of what types of environment in NGC 7331 are bright in both the infrared and in C+, because as I move my spectra around, I'm still seeing that spectra from the C+ FIFI-LS cube. Or I could, right now I'm putting contours on that IRAC data, so I could flip back to the cube and be able to see where the infrared is bright, where the 8 micron is bright, and compare that to where the C+ emission is bright. So this is really useful also if you're interested in trying to find regions that might be potentially interesting in your galaxy. So if you want to specifically extract the flux from the nucleus, it might be hard to see where the nucleus is in your cube, but it can be really easy to see in photometry. So you can get a great idea of both how the C+ emission and the far infrared emission compare, or if you're interested in comparing to UV or optical or some other wavelength, you can do that as well. This galaxy is interesting in the infrared, so I can do that. And I can also start to see where I might be interested in adding, extracting fluxes by looking at this infrared image. So with that, the next thing you'll want to do once you've compared to your photometry is start extracting fluxes. And so I've still got my IRAC data loaded, so I can decide where I want to put my apertures to extract my fluxes. So let me just pause this really quick, maybe. Um, so I'm going to put one on the ring because I'm interested in how the C+ emission from the ring of this galaxy looks compared to other regions. So I'm going to start by going down to this tool, grabbing a circular aperture, and putting it right on my ring in the infrared. Everything I'm doing here is still going to be extracting fluxes from the FIFI-LS cube, even though I'm looking at this infrared image. So once I've done that, I can now set the parameters for my fit. So let's see if I can just back up enough, maybe. Nope, that was not enough. There we go. Ah, so close. Okay. So I press this button here that looks like a little Gaussian with a question mark in order to let SOSPEX know what kind of fit I want to do. I've set my continuum to a constant, which for the C+ line is good enough. And I'm just going to fit a Gaussian, although if you want to fit a Voigt function, that's available too. At the C+ emission line, I'm only looking for one emission line. And there shouldn't be any absorption lines around this C+ line. So I can just say 0, and that lets SOSPEX know what kind of fit I want to do. So once I've set my parameters, I'm going to set where I want the continuum to be. So this is where SOSPEX is going to estimate the continuum. And then SOSPEX pops up this little Gaussian that I can move around and kind of provide some initial guesses to where I think this emission should be. And then I hit this button here to do a fit. It did it, and now I'm just saving the data from that fit in a file that I'm going to call ring aperture, just so I know I'll have all my parameters. This was the flux that I extracted from this aperture in the ring using SOSPEX. And you can save it either as a FITS file or a JSON file. I saved it as a JSON file, but this is just a really nice way to quickly extract fluxes from FIFI-LS data cubes. Once you have that, so this is the saved file. We can see there's a lot of information here, including where my region was, so where the RA and DEC of the center, as well as the size of the region I used and the type of region I used. So there's just a lot of information. If I want to extract fluxes, do photometry, I can just grab this information and know make sure I'm comparing the same region across different wavelength ranges. And then we also have all this information about the line that I extracted as well. I used a Gaussian fit. It gives you a continuum measurement as well as the flux in watts per meter squared. So now I have all the data I need to compare the C+ emission in this aperture from the ring to other emission lines or other emission lines or photometry from this galaxy. So SPECS can also let you compare to other spectra. So I'm going to just load in a local spectral cube. So if I've got some CO data that I want to compare NGC 7331's C+ emission to from the Heracles survey. So I don't get a new tab, but now I can see that I've got this cyan spectral line that is also visible on the spectral panel of this image, so I can see, and that's the CO emission from this galaxy. So this is the 2-to-1 transition from the IRAM data. So now I can directly compare the C+ emission, which is this dark blue line, to the CO emission, which is this cyan line. And one of the things that's really useful here is that I can start looking for areas. This is another way to identify areas of interest. Since one of the things we might be interested in is looking for CO dark gas, so places where the CO emission is not bright, I can see if there's anywhere across my map where I see C+ emission, but I don't see any CO emission. And that might be a space that I'm more interested in investigating more, and just determining what kind of environments we might see that in can also be really useful. So this is a great way, again, to identify regions of interest and also compare the C+ and CO emission across our galaxy disk. So that's just a quick little whirlwind tour of just some of the things you can do using SOSPEX, but it's a great tool for analyzing these FIFI-LS data cubes and comparing C+ emission to photometry and spectra from other sources to get a better idea of what's going on in your data. So once you've done that, I think I said in the beginning, I'm just going to wrap up by talking about a few of the sharing some of the results we got from our paper from useful ways of diagnosing ISM properties using the C+ line. So this first slide is looking at this C+ over far infrared luminosity, which is a really useful measurement because we know that far infrared luminosity is a measurement of dust heating in galaxies, so that C+ over FIR is often used as a way to measure photoelectric heating efficiency, because C+ is our cooling, far infrared is our heating, so C+ over FIR gives us kind of a cooling heating balance measurement. We can see in this plot, though, there's this decrease, and this is another reason a lot of people are interested in measuring C+ over FIR, and this is known as the C+ deficit. And what we can see is that as we go to more infrared bright sources, so sources that have a higher higher infrared surface brightness, there's a decrease in the C+ over FIR ratio. And so understanding why this is occurring is a big question for folks who are interested in using C+ emission as an ISM diagnostic, especially if you want to use C+ emission to measure star formation rate, because we know that far infrared luminosity traces star formation rate. So since there's not this, we'd want this line to be flat, it's not. Understanding why it's not flat is really important for understanding how we can use C+ to measure star formation rate or other ISM properties throughout the universe. Another really useful thing with FIFI-LS, because we were looking at this big nearby galaxy, we were able to spatially resolve different regions within it. And so looking at local universe galaxies, we can compare the difference between nuclear measurements in these yellow points, the measurements from the ring, that really bright infrared ring, and then also measurements from the disk and arms of the galaxy to other local measurements from the Kingfish survey, which were just focused on star forming regions, as well as to the GOAL sample, which are global measurements from ultraluminous infrared galaxies. And this just allows us to see where are the C+ deficits greatest. We see this really low point in the nucleus, which is interesting. And also, where is the C+ deficit having the least impact, which maybe is in these arms and in the disk, where the C+ over FIR is the highest. Another really useful thing to compare C+ to is the polycyclic aromatic hydrocarbon emission, or PAH emission. So PAHs are some of the smallest dust grains in the ISM, and they provide a lot of the free electrons that can excite the C+ emission line in the neutral ISM, and are also one of the really important sources for heating the neutral ISM. So C+ over PAH is also a way of kind of understanding, again, that photoelectric heating balance, where C+ is measuring cooling, PAHs are measuring a very specific heating, so heating in PDRs, and looking at how those are balanced can tell you a bit about how energy is being transferred across the ISM. So this graph here is just showing some of the major PAH emission features. So these aren't emission lines because PAHs are molecules, not atoms, but we can see that there's a really important one. There's a few important PAH emission features in kind of the mid-infrared, one at approximately 7.7 microns and one at 11.3. And we can use these to also understand a bit about the status of the PAHs in the ISM. So this is another plot from our recent paper on NGC 7331, where I'm showing the C+ over PAH emission on the y-axis compared to this this ratio of PAH emission features, so the 7.7 and 11.3 emission line features. And the reason we've chosen to compare to this ratio is because this ratio has been shown to be an indicator of PAH grain charged. So excuse me. So more highly charged grains will have higher values of this ratio. So we're seeing more highly charged grains as we move up on the x-axis. So this tells us that we see this slight decreasing trend, not as obvious as in when we compare to the infrared, but it gives us an idea that maybe these pH grains being charged makes it a little harder to further photo eject electrons from these highly charged pH grains, making them less good at heating the ISM and lowering the photoelectric heating efficiency within PDRs, which could be part of the cause of this decrease in C plus to PAH that we see as we move up in PAH charge. The final diagnostic I want to mention is that it can be useful to compare C plus emission to CO emission to determine how C plus can be potentially used as an indicator of CO dark molecular gas. This is especially useful for low metallicity ISM, where we kind of expect there to be a large amount of CO dark gas, as shown by this beautiful figure from the Madden 2020 paper, as a model of where we might expect to see this CO dark molecular gas. Since molecular gas is kind of the main fuel for star formation, it's important to know how much molecular gas is in your galaxy. But of course, H2 doesn't have any good observable emission. So instead we use CO to determine how much molecular gas is present. But if there's molecular gas that is CO dark, or there is no CO associated with it, we might be missing some of that molecular gas, especially in these low metallicity sources. So we might need other tracers to supplement CO and determine how much molecular gas is in these sources. And that's where the C plus emission line could be a very useful indicator of molecular gas properties, because if there's no CO, we expect there to be singly ionized carbon that will produce this C plus emission line. And so comparing C plus to CO, we can start to look for CO dark gas, and then also use PDR models to diagnose the conditions within the ISM. So these are some archival sources, as well as the data, again, from NGC 7331, where we've compared the C plus over FIR to the CO over FIR. And we can see that for the most part, and then overplotted the PDR models from the PDR toolbox. And we can see that for the most part, the regions within our galaxy fall within the PDR models, so that's CO is kind of emitting as we would expect. But there are also a lot of sources where we did not detect any C plus emission, as shown by these points where we have upper limits on our CO over FIR. And those could be areas within the galaxy where we're seeing some CO dark molecular gas. And they mainly were present in the disk and the arms of this galaxy, but it's interesting that we're even potentially seeing CO dark gas in a solar metallicity, pretty Milky Way similar galaxy. So useful to be able to trace this by comparing C plus and CO emission. Okay, so that's so just as a quick summary, hopefully I've shown that C plus can be a valuable tool for understanding especially the energy balance in the ISM. FIFI-LS on board SOFIA is a great way to efficiently map the C plus line in nearby galaxies, which we can then analyze using the SOSPEX tool and compare to a range of different tracers to understand the ISM conditions. And I mostly focused on data from NGC 7331, shown over here, but these other 4 galaxies, NGC 6946, M51, and NGC 3627, all also have full C plus maps available on URSA from FIFI-LS. So I'm happy to answer questions if folks have any.